Let me welcome you to a new edition of physics. In this edition, we'll learn about electromagnetic induction. I'll explain self-induction, how to demonstrate self-induction, how to minimize it, and we'll be able to solve some problems. So let's get started. Self-induction. Okay, before explaining self-induction, let me remind you with electromagnetic induction. Electromagnetic induction, yes, is the generation of electromotive force in a conductor as a result of the variation of the magnetic field intercepting the conductor. Okay, conductor means straight wire, circular coil, or solenoid. And it is determined by Faraday's laws. EMF is directly proportional to the number of turns. Okay, EMF is directly proportional to the rate of a change of magnetic flux. From the two equations, we can say EMF is proportional to N delta phi over delta T. Proportionality sign is replaced by equality, okay, sign. We expect to have a constant, but the constant has got a value of 1, and we've got a negative sign, and of course you know why we've got a negative sign. It indicates Lenz's rule. So Faraday's law, EMF equals N delta phi over delta T, and we've got a negative sign. And now the negative sign, as I said in the previous relation, indicates Lenz's rule. And now what about self-induction? Definition of self-induction: it is the generation of an EMF in a coil, in a circuit, when the current flowing in the coil, it changes. Okay, when the current flowing in the coil itself, it changes. Okay, the moment the current changes, it will induce an EMF. When the current through a conductor is changed, the flux through it, through the conductor, also changes. And in this way, we've got a changing magnetic field intercepting a conductor, and this will induce an EMF. Okay, now your attention, please. We've got a circuit that contains, yes, a coil connected to a rheostat and a cell, and we've got a switch. Okay, there is a current flowing, the current of the battery. Okay, the moment the circuit is broken, yes, what happens? Your attention, please. The current of the battery collapses, so its associating magnetic field collapses, decreases. Okay, as long as we've got a changing magnetic field, whether increasing or decreasing, this will induce a current. The current, according to Lenz's rule, will oppose, yes, the change producing it, will oppose the decrease, so it will be in the same direction. So here we've got an induced current in the same coil when the field through this coil is changed. Okay. Once again, okay, your attention, please. Compare the two, yes, circuits. Will you please note the rheostat, the position of the slider? So we decreased the resistance. The moment the resistance is decreased, the original current, the current flowing through the circuit, is increased. And this will increase, yes, the magnetic field associating it. So we've got a changing magnetic field once again intercepting the coil. It is increasing, and this will induce a backward current. Yes, a current that flows in an opposite direction to oppose the change. The change is an increase in the magnetic field. Okay, so once again, if you compare the two circuits, yes, we decreased the value of the rheostat. The current is increasing. The moment the current is increased, yes, its magnetic field will be increased. We have a changing magnetic field. It is an increasing one, and this one will induce an EMF. A current is produced, a current is induced. This current will oppose the increase. It is a backward current. And now let's calculate the inductance of the coil. Okay, according to Faraday's, EMF equals negative N delta phi over delta T, N number of turns on the coil. Delta phi over delta T is the rate of change of the current. Okay, this is equation number 1. Also, EMF is proportional to the change of the current. EMF is proportional to the rate of change of the current. Proportionality, yes, sign is replaced by equality. We've got a constant denoted by capital L, letter L. Okay, so EMF is the electromotive force induced in the coil. L is the inductance of the coil. Delta I over delta T is the rate of change of the current. This is equation number 2. From 1 and 2 we can say N delta phi equals L delta I. Of course delta T is crossed out. In this way we'll be able to obtain the inductance of the coil. Inductance of the coil, L equals N delta phi over, yes, delta I. So the inductance equals N, number of turns on the coil, delta phi, change of the field through the coil, delta I, change of the current. EMF, since EMF equals negative L delta I over delta T, where L is the inductance of the coil, we can say volt equals Henry ampere per second. Okay. So first of all, what about self-inductance of a coil? We want to define self-inductance of the coil. So back again to the previous relation. L, we want to define L. L will be equal to EMF when the rate of change of the current equals 1 ampere per second. So I'm defining, yes, the inductance of the coil. What about it? Inductance of the coil is the EMF induced in the coil. When the current flowing through it, through the coil, it changes at a rate of 1 ampere per second. So once again, definition of inductance, it is the EMF induced in a coil. When the current flowing through the coil, it changes at a rate of 1 ampere per second. Henry, what about Henry? Henry is the inductance of a coil. It is the inductance of a coil which an EMF of 1 volt is induced when the current through the coil it changes at a rate of 1 ampere per second. 1 Henry means an EMF of 1 volt is induced in the, yes, an EMF of 1 volt is induced in the coil when the current it changes at a rate of 1 ampere. Henry is the inductance of a coil in which an EMF of 1 volt is induced when the current flowing through it, it changes at a rate of 1 ampere per second. Okay, what's meant by inductance of a coil equals 0.3 Henry. Okay, an EMF of 0.3 volt will be induced in this coil when the current flowing through it, it changes at a rate of 1 ampere per second. Inductance of a coil equals 2 Henry. An EMF of 2 volts will be induced in this coil when the current flowing through it, it changes at a rate of 1 ampere per second. Okay, so we managed to define Henry. Okay, it is the inductance of a coil in which an EMF of 1 volt is induced when the current through the coil it changes at a rate of 1 ampere per second. And now we've got, yes, a question. Choose the current in a 2.5 Henry inductor. 2.5 Henry inductor drops from 7 to 3 ampere in 14 milliseconds. So we've got inductance L. Yes, change of the current from 7, drops from 7 to 3, and this occurs in 14 milliseconds. Milliseconds should be converted into seconds, multiplied by 10 to the power of negative 3. The average induced EMF is it 536 volt, 714 volt, yes, 1250 volt, 780 volt. Okay, what rule to be used? Yes, EMF equals L delta I over delta T. Okay, I'll give you seconds to do it. Yes, it's all easy. It is 714 volt. And now demonstration of self-induction. How to demonstrate, yes, self-induction. In front of you, we've got a circuit that contains an electromagnet connected to 6-volt battery and tapping key. Okay, so the figure shows an electromagnet connected in series with a 6-volt battery and a tapping key. Okay, so we've got a current already passing, flowing through the circuit, through the electromagnet. Yes. Okay, the moment the circuit is broken, a small arc means we've got discharge. A small arc occurs at the switch contacts. The moment, at the instant the switch is opened, we can note the presence of a discharge, a small arc. This due to the high EMF, high forward EMF induced in the coil when the current is switched, yes, off. The discharge is caused by the large self-induced EMF as a result of the collapsing of the magnetic field around the electromagnet. Okay, and now we want to demonstrate how high it is. So neon lamp is connected across the electromagnet and the experiment is repeated. So it flashes the moment the switch is opened. So the high EMF of self-induction is demonstrated by connecting a neon lamp, neon discharge lamp across the terminals of the electromagnet. Will you please note the neon lamp requires at least 180 volt to glow, yet it flashes every time the current in the circuit is switched off. Don't never forget that we've got 6-volt battery. 6-volt battery will never be able to flash the neon lamp, but it flashes due to the forward induced current. Okay, the high one. And now talking about the factors affecting the inductance of a coil. Affecting self-inductance of a coil, what about the factors that can change this inductance? Of course, number of turns on the coil, number of turns of the coil, geometry of the coil, and type of core used inside the coil, and finally the spacing between the turns of the coil. These are the factors affecting the inductance of the coil. Number of turns, geometry of the coil, type of core, and spacing between turns. Non-inductive coils. Now, how to eliminate self-inductance? If we want to get rid of self-induction, if we want to get rid of the current induced by self-induction, we'll use something, we'll use some type of coils, we call it non-inductive coils. Okay, what about these coils? It is quite clear. Non-inductive coil is a coil whose wire is doubly wound. The wire is doubled back on itself before being coiled up. Okay. Will you please note this quite well? And what is the idea behind this? Once again, non-inductive coil is a coil whose wire is doubly wound. This will produce zero, magnetic field, because the current flowing in one side, one branch of the wire will be opposite to that, and the field of one of them will cancel out the field of the other. Okay, this is the idea. Non-inductive coils. Okay, what about it? What about non-inductive coil? By this method of winding, the coil has zero resultant magnetic field. Why? As I said, and consequently no self-induced current is set up. When the current, through the coil, it changes. Okay, because the field due to the current flowing in one branch, in one side, will cancel that produced by the other branch. Give reason. Okay, electric current grows in a straight wire faster than that in a solenoid. Electric current grows in a straight wire faster than that in a solenoid. Okay, why? Yes, since EMF equals negative n delta phi over delta t, Faraday's laws, so EMF is proportional to the number of turns. The greater the number of turns, the higher the EMF induced. And EMF, opposes this induced EMF, will oppose the growth of the current. We've got, number of turns on the solenoid, but we don't have any turns on the straight wire. So it follows the back EMF induced by self-induction in a solenoid is much greater than that, in a straight wire. Okay, the back EMF delays the growth of the current. Back EMF delays the growth of the current. Applications of self-induction. The fluorescent lamp. Okay, what about the fluorescent lamp? Yes, it consists of cylindrical glass tube containing a mixture of argon gas and mercury. Okay, and you can note something here. We've got automatic starter and pull-loss. Pull-loss is an inductive coil, and we've got two filaments here, tungsten filaments at each end of the tube. So the lamp consists of cylindrical glass tube containing a mixture of argon gas and mercury at very low pressure, with the tungsten electrodes, filaments at each end. Okay. The lamp, should be connected to the source of electricity. When it is connected, what happens? The filaments heats up. They give off electrons. Okay, and the question is, we've got very high resistance because of the gases found inside the tube. How to, overcome this resistance? We need a striking voltage. Which, component of the circuit will produce the striking? Yes, it is the inductive coil, ballast. So, when the lamp is first turned on, the current heats the two filaments. The current heats the two filaments. They give off electrons. They also warm the gas in the tube and vaporize the mercury in it. Okay, and your attention please. Soon the starter gets heated. It detects the rise in temperature and automatically opens the circuit. When the circuit is broken, when the starter opens the circuit, yes, the ballast, the magnetic field of the coil ballast, yes, it collapses. The magnetic field is stored in the inductive coil, is discharged in the tube, providing the striking voltage. The electrons emitted from the filaments are forced to vibrate to and fro at high speeds. They collide with the gases. They collide with the atoms of the inert gas. The atoms get excited and produce ultraviolet. Okay. And what about ultraviolet? When ultraviolet strikes phosphors, okay, the phosphors are excited and they give off light of lower frequencies which combine to produce white light. So when the ultraviolet light strikes phosphors, the fluorescent film which lines the tube, the phosphors are excited and fluoresce, giving off light of lower frequencies, which gives the sensation of white light. And now talking about eddy currents. Okay, let's define eddy currents. Eddy currents are induced currents that circulate inside metallic cores as a result of a changing magnetic fields. Eddy currents, induced currents, of course, they circulate inside metallic cores as a result of a changing magnetic field. But they are very intense and associated with rise in temperature. Okay. Eddy currents are induced in a metallic core either by moving the core in a constant magnetic field or by subjecting the core to a changing magnetic field. The question is, how to minimize eddy currents? We cannot get rid of it, but we can minimize it. How? To minimize eddy currents in a metallic core, the metallic core should be laminated to increase the electric resistance. It is divided into very thin sheets. The metallic core is made of thin sheets, thin laminations. Okay. It is shown in front of you. It is laminated core. Each sheet is insulated. The laminations, okay, each one of them, each sheet is insulated from, yes, each other, thus increasing the electric resistance and limiting eddy currents. Okay, also, eddy currents are put to good use. We can, yes, use eddy currents. They are put to good use in the induction furnace to melt metallic cores. Okay, this is the shape of an induction furnace. In this furnace, yes, a current is sent through a coil, but the current is changed at very high frequency to produce very high, yes, very high changing magnetic field. And this field will link the metallic cores placed inside the furnace and will melt it. So eddy currents are put to good use in the induction furnace to melt metallic cores. This is the idea. We've got a coil connected to very high frequency current. Very high, yes, very high frequency alternating current. And now let's, yes, obtain a formula for the EMF induced in a wire. So in front of you we've got, yes, a frame and a wire AB. Okay, the wire has to be, yes, moved so as to obtain a current. And now the length of the moved wire is denoted by L, and the distance moved is delta x, and area where the field is changed is equal to L delta x. And what about the EMF? Delta area, the change in the field occurs in an area equals to L delta x, And the EMF is obtained from, yes, EMF from Faraday's. Thank you very much. So EMF equals N delta phi over delta T. So we want to find delta phi first. Phi equals A, B. And of course delta A equals L delta X. So delta phi equals B, L delta X. And now we'll apply Faraday's EMF equals minus sign here indicates Lenz's rule, and delta phi over delta T. We don't have any terms, so it is equal to 1. So EMF equals negative sign delta phi over delta T. And once again, we managed to obtain delta phi. Delta phi equals BL delta X over delta T. Delta X is a distance. When distance is divided by time, it will give velocity. So EMF induced in the wire equals minus sign BLV. B is the magnetic flux density, L is the length of the wire that moves in the field, V its uniform velocity. In general, the formula is minus L or minus BLV sine theta. B magnetic flux density, L length, V is velocity. Theta is the angle between direction of motion of the wire and magnetic field. In this particular case, it is 90. So it is equal to BLV. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Stay safe. All the best for you. Bye.